let's continue with our main attraction. So it's my great pleasure to introduce the JDC plenary speaker, Lilia Maliar. So the JDC has been sponsoring for decades one of the plenaries at the CEF to highlight, to reward outstanding and long-lasting contributions in, well, economic dynamics and control and the computational methods that are used in these fields. And in my mind, Lilia exemplifies everything that the JDC stands for, likes to publish papers on, especially through her involvement with the society and with the JDC. So Lilia earned her PhD in 1999 at the University of Pompeu Fabra, and via appointments at the University of Alicante, Stanford University, she is now professor at the Graduate Center of the City University of New York and a recent visiting fellow of the Hoover Institute. So without further ado, let me welcome Lilia, and let me turn it over to her. Thank you.
Thank you so much, Thomas, for this kind presentation. So I would like to thank organizers for inviting me and the JDC for sponsoring this session. So I would love to be in person now in Dallas. I was planning to come, and I was unlucky enough that for 2.5 years I didn't have COVID. And in the morning when I wake up to go to Dallas, I tested positive. I don't believe that it's possible, but it happened to me. Okay, so now in my room, I'm trying to mimic presentation as much as possible. So let's start. So I'll share my screen. So the title of the presentation is Deep Learning for Solving Dynamic Economic Models, Theory in Applications. So before I start, I would like to explain the structure of the presentation. So I'll have two parts. First part will be about theory or solution framework. And the second part will be more about applications. So the first part will be based on a joint paper with Sergey Maliar and Pablo Vinant. And this solution framework will include the following ingredients, like multi-layer neural networks, stochastic simulation, effective integration on random grids, batch gradient descent training, parallelization, and implementation with Google TensorFlow. We are going to consider two applications. Our two example will be consumption saving problem with borrowing constraints. So this is because neural networks are very flexible, and if they have more advantages relative to polynomials, this is exactly in the context of models with inequality constraints. And the second application is a standard Crusoe-Smith model. We solve this model with 1,000 agents or 2,001 state variables. So applications, I will have time only to focus on the first two. In the first, we apply classification to solving discrete labor choice models. In the second, we solve Hank model with individual and aggregate stochastic volatility. And the other two applications, so in one of them, we solve Hank and classical model with heterogeneous agents with bonds, and also central banking model by using deep learning. Okay, so let me start from part one. As I said, it is based on our recent paper published in Journal of Monetary Economics. So I should say that we began this project about 5-6 years ago, and we were very optimistic on how to like incorporate machine learning techniques into economics for solving dynamic economic models. So for us, it was evident that there is a lot of similarity between AI and economic agents. So AI is a device that has a goal. Think of computer games. So when we play a game, we want to win, no? And then AI perceives its environment by maybe studying the environment and then takes actions to achieve its goal to win the game. And this looks exactly like an economic agent, where we have a goal to maximize, let's say, utility or profit. Environment is described by state variables, and actions are given by controls chosen by the agent. So given this similarity, it's reasonable to hope that AI is very helpful for economic dynamics. And we see really impressive applications of AI in everyday life, like self-driving cars, computers write music, image recognition, and so on. So the hope is that we can use all these known techniques and apply them in economic dynamics. So in economics, we have quite many difficult economic models, like games or models with inequality constraints, and so on. And so it would be kind of nice if we can solve those difficult models by using the existing technique in machine learning literature. And moreover, it will be even better if we are able to come with some general purpose code that would just need to plug in any model and give us a solution. So this is the hope that we had. So in this paper, we have 4 main results. So first thing to think is how to map economic models into deep learning objective function. And so in this paper, we offer a unified approach forecasting objects of economic dynamics into this deep learning objective function. So we have 3 main objects: lifetime reward, Bellman equation, Euler equation, and we show how to cast them into the objective function of deep learning. Then we show how to solve economic models on random grids, stochastic optimization. This allows us to solve large-scale models. Then we introduce a special operator that allows us to compute expectations. We call it all-in-one expectation operator. And then we use Google TensorFlow software that led to break ground applications in data science, and we provide codes on Quanticon website. So alternative for Google TensorFlow is PyTorch, and you can find examples of the codes from Mark Maliar's website. As I mentioned, we solve Crusoe-Smith model with 2001 variables. How is it possible? 3 features of our framework allow us to do it. First, neural network performs model reduction. In particular, it is able to extract information from many inputs and condense it into a small set of hidden layers. Then everyone knows that ill conditioning could be a severe problem when solving the model. So neural network deals with ill conditioning again automatically. It ignores redundant and collinear variables. And finally, by focusing on the area of the state space where a solution lives, and by using stochastic simulation, we are able to solve Crusoe-Smith with 2001 state variables. So the literature that used neural networks for approximation dates back to Duffy and McNeilis. This was a paper published in 2001 in JDC. And recently, there are few new papers that use deep learning for solving the models, like Duarte, Fernando Villaverde et al., Villa, and Valaitis. So the contribution of this paper was to show how to cast the entire model into deep learning objective and how to solve it with TensorFlow. And so related deep learning method is developed in Azinovich et al. So I will present some background very briefly, given the shortage of time. So background on deep learning. So deep learning models are based on artificial neural networks, which are created by analogy with human brain. So human brain is connected with, in human brain, neuron is connected to other neurons through connections. And this is exactly what we have in artificial neuron. So we have here an example of a network consisting of input layer, hidden layer, and output layer. And so each neuron in the hidden layer is connected to other neurons, and the strength of connections is measured by coefficients theta. Then each neuron in this hidden layer performs computations using an activation function and passes the information to the output layer. We can use different activation functions to perform computations. So one thing to observe is that in a neural network, each level learns to transform its input data into a slightly more abstract and composite representation. And when we say deep in deep learning, it means that we basically have multiple layers through which the data are transformed. So neural networks, they are known since 50s, but they only become popular in recent times because of the ability of computers to include multiple layers. So these are examples of activation functions used by neurons to perform computations. And the most well-known examples are sigmoid and ReLU function. So sigmoid function is convenient because it is bounded between 0 and 1, and it allows us to get probabilities, let's say, or if we want our variables to be bound between 0 and 1, this is convenient representation. So some background on ergodic set. So we solve models by using stochastic simulation. And from the previous literature, it is known that when you deal with high-dimensional problems, it's convenient, or it's the only way to go, is to focus on this state space where the solution lives. So we call it essential ergodic set or ergodic set. So in this figure, an example of optimal growth model where ergodic set takes the form of oval. So if you focus on this blue area instead of rectangular area, so you save a lot on cost. So in two-dimensional, the saving is not particularly large. Let's say if you, instead of oval, use a circle and inscribe a unit circle into a unit square, then the area of circle to square is 79%, so the saving is 21%. However, for such a dimensional case, the saving will be almost 100%. So for high dimensional problems, when we focus on ergodic set, we save a lot in terms of cost, and so we just face a tiny fraction of the cost that we would have faced on a fixed hypercube grid. So background on the training of machines. So in many optimization problems, we use gradient descent, in which coefficients are updated in the direction of gradient descent. So the first formula tells us that on a new iteration, coefficient is previous iteration minus gradient of expectation of the functions that we want to optimize. And so it's costly to compute true expectation, so that in machine learning, people use cheaper versions, which is called stochastic gradient descent. So instead of computing true expectation, we just randomly choose the direction in which we want to change theta into direction of gradient descent, and then iteration after iteration change the direction. So here lambda is the learning rate. So another version would be batch stochastic gradient descent, in which case we consider n's different directions. So this is just an example that shows that different stochastic gradient descent methods will take different routes and then converge to the optimum. So a deep learning algorithm for optimization. So we were trying to find similarity between economic model and AI algorithm. And actually, there are many similar things. So in particular, we can frame or represent AI algorithm for optimization in general form and try to mimic it when we solve an economic model. So each algorithm contains 4 steps. First is to define an objective function. Think of a regression when we want to minimize sum of squared residuals. So n will be your data points, and this C represent the like residuals, squared residuals. And so we need to find a functional form in the second step for this hypothesis that minimizes the distance between your X observation and Y observations. And so in step 2, if we use for phi neural network, then it will be deep learning algorithm. Then we train the machine by finding theta that minimizes the objective and check accuracy. So in economic models, we need to also perform the same steps, but we need to think how to specify this objective. So, as I said, our toy example in this framework was consumption saving problem because it does have borrowing constraint. So this is a standard consumption saving problem with constant interest rate. We include here 4 shocks. The borrowing constraint says that consumption is smaller or equal than cash on hand. So each of the shocks follows first order regressive process. We form a vector Z out of them, and it also has the same structure. And so because of borrowing constraint, we need to write Kuhn-Tucker conditions. Let's H be Lagrange multiplier, which is defined here. And so complementary slackness conditions would require that a borrowing constraint is satisfied, Lagrange multiplier is greater than 0, and the product of these 2 is equal to 0. So we also can write Bellman equation. So as I mentioned, so we propose how to cast 3 objects of economic dynamics into deep learning objective function. So let me briefly describe the ideas behind different objectives. So the first objective is lifetime reward maximization. So what we do is to parameterize consumption function by using neural network. And then we construct the objective, which is basically lifetime utility. And this is my empirical risk or objective function. And so expectation is with respect to the following random variables. So in the first place, Z sub 0 W0, or which will be initial conditions for shocks and cash on hand. And then epsilons will be innovations, future innovations. So by construction, this objective function leads to a randomness of 2 types with respect to state and with respect to innovations to be in the same place. So why do we solve models by considering like different random initial states? Because we want our model solution represent well the general solution. So in case when expectation operator contains all randomness, we refer to this case as all-in-one expectation operator, and we'll see how it is important to have it in other cases as well. So these are the results for this case. So on the left side, Euler equation residuals over the iterations that appear on the right side, and then lifetime reward on the right panel. So all different stochastic gradient descent methods converge to the same level. So the second objective is related to Euler equation, and we thought of minimizing Euler equation residuals. So in our case, we have also Kuhn-Tucker conditions, which we found convenient to represent with a so-called Fischer-Burmeister function. So we know that with borrowing constraint, so we have non-differentiability, but if we replace our complementary slackness conditions with this function, it allows for differentiability. In particular, this function depends on A and B. It's a functional form for it. A and B should be greater than 0, and the product is equal to 0, exactly as in complementary slackness condition. So for us in the model, A will be given by left side of the borrowing constraint, and B by the Lagrange multiplier. So objective function for this case would be just residuals in the Fischer-Burmeister function or in complementary slackness conditions. And one thing to notice that now expectation with respect to a random state and in future innovations are separated. In particular, we have expectation with respect to innovation inside the square, so we cannot take it out. And this is inconvenient and gives problems. So similar results for this objective too. So you get quite low residuals, especially for this red line, which is called Adam method, and all the methods converge to the same solution. So finally, objective 3 is based on Bellman equation, and we minimize residuals in Bellman equation. So for this, we will have to construct two neural networks for value function in terms of theta 1 and for consumption function in terms of theta 2. We draw initial state and define the objective consisting of two parts. One represents residuals in the Bellman equation, squared residuals. So there is a left side and the right side of Bellman equation, and the other is just objective function of the Bellman equation, again, this squared. And as you can see, both terms have the structure that expectation with respect to random state and innovation are separated, so we cannot take the second expectation outside of the square, and this brings some problems. So it's not all-in-one expectation operator. So the results are the same. So the model is able to reproduce the kink in the consumption function, and the solution is quite close to the true solution, which is given by this dashed line. So let me say a few words about all-in-one expectation operator, because it's really kind of essential to have this result for high-dimensional problems where computing expectations is very expensive. So first, as we saw for objective 1, it's naturally all-in-one expectation operator, and for objective 2, it's not, because two types of randomness are separated. In particular, we want to know this term. And what we have in parentheses is just expectation, which is repeated 2 times. No? And as I mentioned, we cannot take this second inside expectation outside of square. So this will create problem when we use stochastic gradient descent, because once we need to compute the gradient, so we cannot switch the order of expectation and take it out of the square. And so the contribution of that paper was to show how to deal with this so that stochastic gradient descent is not biased. So what we did is to replace, I will show again the terms that we had here. So we need to compute expectation, and then inside of parentheses, expectation of f. So it's basically EF 2 times. And so what we did is to replace that EF 2 times by just this integrand evaluated in 2 randomly drawn innovations, epsilon 1 and epsilon 2. So given that they are independent, we can write this product as just expectation with respect to epsilon 1, epsilon 2, and then the product of this f evaluated in epsilon 1 and epsilon 2. So the good news is that with this the trick, the stochastic gradient descent is unbiased, and therefore, there's a cheap way to evaluate the gradient. So for Krusell-Smith model, we consider a version with some given number of agents. So we have identical agents. They differ in productivity and capital. We have a borrowing constraint on capital, and now interest rate and wage are time dependent. So agents are hit by idiosyncratic productivity shocks, which follows first order autoregressive process. So there is aggregate uncertainty in production function. We have this TFP shock, the T, which follows first order autoregressive process. And the true state space include this TFP shock in distributions for capital and idiosyncratic productivity. So in the seminal paper by Crusoe-Smith, they proposed a method that allows to solve heterogeneous agent models of this type with distribution. In particular, they replace distribution with a finite set of moments, M, and then approximate state space by individual state, aggregate TFP shock, and moments. So the distinctive feature of our result was to work with the actual state space. Let me just show one objective. It's objective of type 2 when we use Euler equation. And so suppose we denote by K distribution of capital, by capital Z distribution of productivity, and then sigma 1 and sigma 2, these are just independent innovations for L agents. And then in the objective, we minimize residuals, which are residuals of the same Fisher-Burmeister function. And then the second term with some weight V is just my Euler equation. Okay, so these are residuals in the Euler equation. And so for solving the model using true state space, the procedure is as follows. So we draw initial state Z for TFP, and then distributions for K and Z. Then we compute aggregate K given a distribution and aggregate prices. We train neural network for L agents. And then we compute next period distribution using the decisions of all heterogeneous agents. And then we proceed iteratively until convergence. So the reasons for this result, so that we can solve this huge model, I mentioned before. So I said that ergodic set domain is important. So working with stochastic simulation kind of allows us to deal with the course of dimensionality. Then in the decision rules, we include individual variables 2 times. So once we specify the decision function of each agent, and the time when we specify the distribution. But because neural network can handle multicollinearity, it's not a problem for it to deal with this problem. And then model reduction. So when we have this 2001 state variable, neural network condenses those variables into 65 neurons in each hidden layer, which allows us to reduce the model automatically. So these are the results. Let me just point out that consumption function does have some kind of kink, and the different lines correspond to different levels of productivity of different individuals. So let me then focus on other applications. So let me start from application that was recently published in the Journal of Economic Dynamics and Control. And this is joint work with Sergey Maliar. So in this paper, we try to apply a technique from machine learning, which is called a classification method for solving models with discrete labor choice. So this is how in this picture, you have your data and you want to classify your observation, let's say in 2 classes, men and women. No? So a classification problem, it's a problem when you need to work with like discrete variables like 0, 1. No? So macroeconomic models are generally built on the assumption of continuous set choices. So we know many examples when, let's say, agent needs to distribute wealth in any proportion between consumption and savings, or when choosing how much to work and how much time to have leisure, the agent distributes time endowment in any proportion. But in many interesting economic models, the choices are not continuous but discrete. Examples would be buying house or not buying house, being employed or unemployed, to retire or not to retire. And so in this paper, we propose a deep learning classification method for models with continuous discrete choices. So to explain the analogy with data science, let us think of three-class classification problem. So consider a typical image recognition problem when machine needs to classify images into, let's say, dogs, cats, and pigs. No? And so what it does is to parameterize the probabilities of these three classes with a deep multi-layer neural network, compute these probabilities, and then select images with the highest probability using a softmax function, which is a generalization of sigmoid function for multi-class classification. Then we feed into the machine a collection of images, train the machine to maximize the likelihood function, and this presumably will ensure a correct classification. So we try to mimic the same procedure for solving the model with discrete labor choice. In particular, we focus on a version of indivisible labor model. So as you know, the original model was proposed by Rogerson and Hansen, in which lotteries decided who is going to work and who is not. No? In our case, we don't have lotteries, so the agent, or we compute the probability of being employed, and then assign a worker or an agent to work or not to work, depending on the value of the probability. So the highest probability will point to the outcome or to the state of the agent. The idea is similar to what I have described for classical classification problem. So we just parameterize the state contingent probability to work with a deep neural network. And then we check if a probability that the agent's wage is higher than her reservation wage is larger than 1/2, then this agent, according to this probability, should choose to be employed. And if it is smaller than 1/2, then unemployed. Then we compute wages and employment decisions for all heterogeneous agents. And then we train the machine to maximize the likelihood function that matches ex ante and ex post labor choices. So we work with the same Crusoe-Smith models that we have seen before by adding just labor choice. So utility does include valued leisure now. And the rest of the problem is the same. So we have idiosyncratic productivity shocks, borrowing constraint, and time variant interest rate and wage. So this variable NTI can be either divisible, any number between 0 and 1, or indivisible, so 0, 1 if the agent is unemployed, 0 if employed 1, or we can also add the third state, let's say part-time employed. In this case, 0, 1/2, and 1 will correspond to being unemployed, part-time employed, and employed. So this is a result for divisible labor model. So let me just comment on labor rule. So as you see, again, so these lines correspond to different agents with different levels of productivity. So when agents are poor, which is represented on the horizontal axis, then all of them choose to work a lot. But then as they become richer, this blue line so tells us that the higher productive agent, he actually decides kind of not to work less and less relative to the other agents because he is highly productive, and this is the outcome. Okay, so let me talk about how we model classification problem, and this is a typical picture from data analysis when we have two classes, blue dots and red crosses, and we want to classify this data or separate this data into two classes. So the goal is to construct this separating line or dashed line that that allows us to separate two classes. So let's say class 1 and class 0. So the line separating should not be necessarily straight, but can be some nonlinear function. And steps of the logistic regression. So we first form a hypothesis for separating line. So in my previous slide, a straight line would mean this initial hypothesis, so that x theta is equal to 0 on that line. If it is greater than 0, so we are above this line, y is equal to 1, so we have blue dots. Otherwise, y is equal to 0. Then we need to find a way of mapping probability that a data point y belongs to class 1, and this probability should be related to this hyperplane x theta. So this g function is usually chosen to be given by this log function that I have written in the slide. And so the logistic regression is an optimization step, thus maximization of log likelihood by considering product of probabilities across different data points I. So this is exactly what we are doing in our application with indivisible labor model. So here I have more details on how we proceed with computing probabilities. So we parameterize probabilities using neural network, and then we compute them. And if probability is higher than 1/2, we say agent is employed. Otherwise, he's unemployed. Then given individual choices, we compute aggregate labor, aggregate prices, and restore remaining individual and aggregate variables. And as a final step, we need to check consistency with maximum utility that these choices give us. In particular, we restore value functions of employed and unemployed. So here S represents individual state. And then we check if among two values, value function of employed and unemployed, the maximum is VE, then agent should be employed, and otherwise unemployed. So we check the consistency with what we have received in the initial steps, and if there is inconsistency, so we proceed iteratively and until we get this consistency. So these are results for indivisible labor model. So for capital decision rule and consumption decision rule, we have some spikes. And this is related to the fact that as agents accumulate wealth, they might decide to kind of switch the state from being employed to unemployed all the time. So if you look at labor rule, you see that all agents in the beginning, when they are poor, decide to work the total amount, so equal to 1. But then as they accumulate more wealth, so the one that is most productive, so he just switches. And so basically, depending on the productivity, different agents decide at different levels to work 0 hours. So if we have 3 states, then again, spikes in capital decisions and consumption decisions, but labor rule takes different form with several steps. So first, they all work all the time, but then they work part-time, and then they work the 0 time. So further applications of this classification method would include models with discrete choice. So we have in this paper only one example, but this could be also used for a variety of other applications like sovereign default models, models with retirement, models with indivisible commodities, for example, housing. So let me briefly outline second application about individual and aggregate stochastic volatility. So this is a joint work with Yuri Korotnichenko, Sergey Maliar, and Christopher Nobert. So, and the motivation for this work was related to major recent developments in macroeconomics. So in recent times, macroeconomists incorporate in their models the following features like heterogeneity in income or productivity, assets with different liquidity, machines or liquid bonds. Then modeling aggregate and idiosyncratic uncertainty is done right now in the economic literature. So people are more concerned with global solution methods, especially after a great recession, when people try to account for zero low bound, and finally redistribution across agents. So usually these features are done in isolation in the literature, and this paper tries to incorporate all of them in one framework. So this is the outline of the Hank model. So we have households, firms, and government. Households have two assets, bonds. In a sense, they are liquid in the sense that they do not require payment of adjustment cost when the agent wants to change the holdings of bonds. And machines are illiquid because of such adjustment cost. There are two borrowing constraints, one per each assets. Then idiosyncratic shocks are to both level and variance of shocks, and wages are sticky. So for the firms, we assume constant return to scale with machines and labor, and similar to idiosyncratic shocks, aggregate TFP shocks are both to level and volatility. So for the government, fiscal policy is modeled as progressive income taxation, and central bank follows Taylor rule subject to zero lower bound. So these are just the specifications of the random processes. Let me just point out that in the shock to the level of productivity at both individual and aggregate level, so volatility is time dependent, and each of these volatilities for individual and aggregate processes, so it follows first order of the regressive process. And so there are papers that have similar questions, and so let me just say a few words how we differ from this literature that also incorporates uncertainty shocks. So in the first place, these papers, they work with MIT aggregate shocks. So they are not in the solution procedure, but only when impulse responses are constructed. So these papers, they often consider low order perturbation and consider reduced state space approximations. And so the distinctive feature of the paper is to address these problems using AI deep learning. In particular, we do not work with MIT shocks, but consider aggregate shocks in the solution procedure. And then we compute global nonlinear solutions by using deep learning framework I've just described. And finally, we work with a true state space similar to the Krusala-Smith application that I have presented before. So we look at distributive implications of this model. In particular, this table presents Gini coefficients for wealth, consumption, and net income. So we are slightly below in terms of value for wealth Gini, predicting 0.66 relative to 0.79 as in the data, and then we correctly predicts that income Gini is lower than wealth Gini and consumption Gini is lower than the other two. So we construct generalized impulse responses following techniques described in Coop et al. So for the figures, I consider a model with only TFP risk, no idiosyncratic risk. So this shocks to level. And then compare individual uncertainty shock with aggregate uncertainty shock. So time period in this case is 1 quarter, and we have 200 agents in the solution procedure and in the simulation procedure. So I will show just a few examples. So my basic conclusion is that the individual uncertainty shocks, they are more important than TFP uncertainty shock. So there will be more differences for orange line than for blue line. Let's say for wealth, aggregate wealth, on the impact of individual uncertainty shock, aggregate wealth decreases, but it starts gradually increasing, while there is a kind of flat, almost flat line for TFP uncertainty shock. For Gini, we have an increase in Gini on the impact of individual uncertainty shock, and then it decreases, and there is like a smaller change for TFP uncertainty shock. Now I'll skip the results, other results. I'll just say in conclusion that, as I have mentioned, that responses to individual uncertainty shock is much larger than the response to TFP uncertainty shocks. Individual uncertainty shocks lead to a persistent increase in wealth following an initial reduction, and individual uncertainty shocks increase income inequality. So in future versions, we are working on the model in which individual and aggregate uncertainty are correlated. So let me move to the conclusion in the remaining minutes. So as I mentioned, when we began this project, we were very optimistic, and we're still optimistic, but maybe a little bit less, because it turns out that the things are not as easy as it looked in the beginning. So I have two parts of my conclusion: enthusiastic view and a bit less enthusiastic. So on the enthusiastic side, I would like to say that yes, it is helpful to use all those powerful techniques available in other fields, like classification or deep learning. In addition, it helps a lot to use some general purpose software provided, let's say, by Google, TensorFlow. Without it, it would be impossible to solve these huge models. And given that economists usually very resourceful, but they kind of write like model-specific, not portable code, looking at the existing technologies in other fields would vastly expand the possibility of economic profession. I think the contribution of our work was to show how to cast economic models into the state-of-the-art deep learning methods and software. And we hope that this approach augments vastly the set of models tractable in economics. So on the negative side, there could be different things. So one thing, you can work on your code for weeks, months, or even years, and it finally works, but the results are garbage. So you don't know how to interpret it. So this is one thing. Another thing, so there could be many reasons why it is hard to make the code work. This implies that it is not clear whether our deep learning method is the best possible for solving economic dynamic models. First, it's really hard to make these codes work because on one side, neural network, even though it is universal approximator, as people say. It still has a large number of parameters, and it's very highly nonlinear, so it's not clear how to tune up all those parameters. Then, as we use stochastic simulation, so we know that Monte Carlo integration has a low square root of convergence. Then when we use stochastic gradient descent, the fact that we have only one random direction in which we change coefficients, obviously is not guaranteeing that this optimization method is going to work. It has low convergence rate. And finally, so there could be many other promising AI technology that can be used for solving economic models. So we don't see much, for example, applications of reinforcement learning to economics, although I've seen on this conference in the program, some papers have really nice applications of reinforcement learning. So maybe again on the positive side, so given that it is hard to propose all purpose procedures that would solve all models, and it's not feasible at this stage, it's more like magical thinking. So still by like right use of the knowledge experience of computational economics, so we can progress much, and we can achieve a lot by solving such huge models like Crusoe-Smith model with thousands of agents. So we just don't need to kind of give up. That's it. This is it. Thank you.